chapter 15 is about this concept called equilibrium. We're going to define it as when reversible reactions reach the same rate. So we begin by defining what equilibrium actually is. And the fancy definition is that when the forward rate equals the reverse rate. So first we begin talking about what do we mean by reversible reactions. So in a reversible reaction, we consider that the reaction can proceed in both the forward direction and in the reverse direction. The reactants can make products, but once products exist, the products can also unreact to make the reactants. So we have a forward and a reverse reaction. We will use double harpoon arrows to indicate a reaction that has significant amount of reverse reaction happening. So when we write just a single arrow to the pointing towards the products, that's indicating we're not considering reversibility. We're really just considering as if all the reactants finish reacting and make products. When we see that double harpoon, we're saying the reversibility of the reaction starts to have a significant play. It often also means that when you see those double harpoon reactions, it's indicating this is a reaction that has reached equilibrium. That's frequently implied by the double harpoon. So pay attention to the arrows. So we can think about an example where we have a weak acid, say HF. So HF, we know acids break up and dissociate into H plus ion and then the remaining whatever is left. So we could write this as the forward reaction would be the K of the reactants raised to their coefficients, especially if it was an equilibrium elementary step. But also sometimes the ions can recombine and form a covalent bond and reform the acid. So the reverse reaction can happen too. It has a rate. The rate would be its rate constant of the reverse rate times the concentration of the products raised to their coefficients. Again, assuming that whatever they are, this would be the kinetics. So fun fact, at the very beginning of the reaction, there is no products. The reverse reaction can't happen because there is no concentration of products, but we have a large concentration of reactants. Since the rate is proportional in some way to the concentration, if we start to react those reactants, the concentration decreases, thus the rate decreases. So the forward rate reaction is going to be decreasing as the reaction happens. Similarly, at the very beginning of the reaction, there are no products, so there is no reaction, there is no rate happening. But as products are made, now they can react to form the reactants. So as more and more products are made, the concentration increases since the rate is proportional in some way related to the concentration of the products. The reverse reaction rate is going to increase. It's going to speed up as the reaction goes along. So you can imagine there's a case at which the forward rate, which is getting slower and slower and slower, and you have the reverse rate getting larger and larger and larger, where the rate of the forward reaction equals the rate of the reverse reaction. When that reaches that case, we're going to say this reaction is in equilibrium. And what does it mean? So when this forward rate equals the reverse rate, it now means that the concentrations of all the reactants and products, all the chemicals in the reaction are going to remain constant. Doesn't mean they're the same, but they're going to remain constant because as the forward reaction is making product, the product is now making the reactants as well. So they're kind of canceling each other out so that whatever they happen when they reach equilibrium, those concentrations are now going to not be changing. A common misunderstanding is that people think, oh, the reaction stops. It doesn't stop. It's just that the forward reaction is canceling out the reverse reaction. And so it appears as if nothing is changing, but it's still ongoing. So for every forward reaction, a reverse reaction is happening and undoing it. And we can see if we looked at the example, this is showing the reaction would be, since I have at the beginning high concentration of H2 and I2 and no concentration of HI, this is hydrogen plus iodine making hydrogen iodide product. And you can see at the beginning, I'm going to have reactants are going to be decreasing in concentration because they're becoming products. The products are going to be increasing in concentration. And I get to some magic point where I don't see the concentration changing anymore. When that has happened, that's because it's reached equilibrium. In this case, the forward rate and has become equal to the reverse rate. So let's think about what that implies as well. Again, to be careful, the forward rate equals the reverse rate. But remember, rate is much more complicated than just the concentration of reactants and the concentration of products. So it does not mean that the concentration of reactants equals the concentration of products. In fact, that's almost never true. So the concentrations are not changing, but they're not equal to each other. However, the rates are equal to each other. Another way we can think about this is thinking about two rooms. So room 1, kind of playing the role of the reactants, has 24 students in it. Room 2, playing the role of the products, has 18 students in it. So if I take 4 students leave room 1 and go to room 2, but at the same time 4 students leave room 2 and go to room 1, I can ask some questions. Are the number of students remaining, are the students remaining in the same rooms? No, we had some students moving. So if I were to take a photograph of it, it wouldn't be the same 24 people in room 1, nor would it be the same 18 people in room 2. Some faces would have changed. So that's saying that there is still motion happening. The reactions are still happening. Is the number of students in a room changing? No, because the 24 students in room 1, 4 left, but 4 came. So that cancels each other out. It's still going to be 24. Similarly, in room 2, there was 18, but 4 left and 4 came. So it's still 18. Are the total number of students in each room the same? No. Room 1 has 24, room 2 has 18, so they're not the same. It just means, however, that the 24 is staying 24 and the 18 is staying 18. That's what we mean by equilibrium. Hopefully this gives you a better analogy of what we think about when we talk about equilibrium.